This is going to be the second lecture about p-adic spaces. And so these p-adic spaces, they were associated to these f-adic rings. And Arthur August asked me last time about a certain property that is implied by finitely generated ideal of definition. I wanted to recall this lemma because it's good to know. So the lemma is the following. So if A is any ring, M is any A module, and I is a finitely generated ideal. Then, if I let M hat be the p-adic completion of M, then what you think should obviously be true is actually true, but for non-obvious reasons. Then if you divide this again by I, then you just get the quotient of M by I. So in particular, this implies that M hat is still p-adically complete. Well, is p-adically complete. Because then the same property will hold for all powers of this ideal, and so if you again make this completion here, you just get the same terms. And I don't want to spoil your fun of trying to prove this, so just give a reference. So this is in the Stacks project in section 1091. I don't remember the lemma, just go to the section.
Quickly. I'll hyperlink it. Is it more clickable?
So whenever I try to prove that at home, I'm getting totally confused and can't do it, but it's true. But if you look up the proof, it looks extremely simple. But well, anyway. Okay, so this is one reason that it's nice to have a finitely generated ideal of definition. So if you somehow p-adically complete, then the result is somehow what you think it should be. Huber, I think, didn't enforce this conditional finitely generated ideal for this reason, but instead because for some topological considerations about his p-adic spaces, it was necessary to have such a finitely generated ideal of definition. Anyway, so what I will do today is define a structure sheaf. Or pre-sheaf, maybe in general. On static space. And so, again, let me give a reference. So this is in Huber's paper, generalization. Of formal schemes. And rigid analytic varieties. Okay, so let me recall from last time what kind of rings we were considering. And so in particular, last time I really realized that I don't like this name f-adic ring because it sounds like an adic ring which is f-adic for some element f. And so...
Well, you had some g-adic rings.
Yeah, right. So, I mean, I wanted to call this element f, but then I realized it would be a really bad idea. So, so let me from now on call them Huber rings. That's worse? You don't like it? Well, I like it. open subring A0, which is adic. So finally generated ideal of definition. And then really we were considering these pairs AA plus, and maybe let's call them just the Huber pair. I don't know. Here I'm really taking suggestions for better names. So A is such a Huber ring, and A is an open and integrally closed subring of the power bonded elements. And then to this we have associated a topological space consisting of equivalence classes of continuous variations. Continuous variations on A, which are at most one on these integral elements. And I stated the theorem of Huber that X is spectral has a topological space, which means that X is quasi-compact. Something called sober, which means that every irreducible closed subset has a unique generic point. And then a condition that there is a nice basis for topology, namely a basis consisting of quasi-compact open subsets which are stable under intersection.
I'm confused. When you already defined topology on X? You said there's a basis.
I did define it last week. So the topology is generated by open subsets of the form the locus where inequality like this is satisfied for F and G and A.
So are these, is that?
But these are not quasi-compact in general. And so something I'm going to do in a second is explain to you what such a basis for topology is. It's given by so-called rational subsets of X. I said last time that if X is a spectrum of some ring, then it satisfies these properties. And so as a basis for topology in that case, you could just take the open subsets where some function is non-zero. The usual open subsets. Let me also note that this adic spectrum doesn't change under completion. So if I let A hat plus be the completion of A hat plus, then you get an associated map. This is homomorphism.
Can you repeat what you said about the basis for open sets given by non-zero? I didn't get that.
Well, if X is a spectrum, the usual Sariski spectrum of some ring R, then you have the open subsets given by the non-vanishing locus of some function. And they are quasi-compact open subsets, and they are stable under intersections because you can just multiply the functions.
But here it's not so obvious.
Here it's not so obvious, and as I said, I will explain in a second what such a basis is.
Is completion of A plus still integrally closed? Is completion of A plus still integrally closed?
Yes. And so it might be that I sometimes forget to mention this, so today all 2-by pairs will be complete. Because it won't change anything. So let me first note that the p-adic spectrum is large enough to see important properties. So a priori it's not clear that it's non-zero. So first of all, if A is non-zero and complete, then this p-adic spectrum is non-zero, non-empty. Secondly, you can recover this substring of integral elements as those functions in A, such that for all x in this p-adic spectrum, the absolute value of f at x is minus 1. And then the third property, which probably follows from the first, is that if you have a function f in A, then it's invertible if and only if it's non-zero at every point. I guess equivalently one could say that the map from the p-adic spectrum to the Zariski spectrum, which sends any valuation to its kernel or support, then this map is surjective at least onto the maximal ideals. So now let me talk about these rational subsets. And so in this big generality of p-adic spaces, which also includes formal schemes, the definition is a bit, well, it involves a lot of things. So you take some finite collection of elements of A, and finite subsets of A, such that the ideals I generate in A are open. Then you define an open subset denoted in the following way. To abbreviate, I will also sometimes just write U of the set of the T I over Si. So it's the following open subset. It's a set of all x, such that for I and for all elements in these finite subsets, this inequality is satisfied. So it's clearly in the finite intersection of open subsets, so it's open. But whenever you require some condition that some SI is bigger or equal to something, then actually you require such a condition is not just required for one element, but for a set of elements which generate an open ideal. And I'll try to explain why this is useful. So that's called a rational subset. Also, by definition, if you intersect two rational subsets, then it's a rational subset again because you can just add those two sets together. And so the theorem is that any such rational subset is actually the adic spectrum of another ring. So they come with a complete Hooper pair that I will denote. Well, it comes with a morphism from AA plus into it. And I will denote it by x of u or x plus of u. What is the universal property? The universal property is that the map on adic spectra factors over u. And it's universal for such. And actually for this universal pair it's also true that this map is in homeomorphism. Onto u. So in particular,
Homomorphism of Hooper pairs. What's the definition of a homomorphism of Hooper pairs?
well, it's just a continuous map
Continuous map.
which sends A plus into
Okay.
B plus. So I should say that apart from the stack project reference, the only reference that I know is August Caesar's, where this is probably not explicitly stated but follows easily. Okay, so if you admit that the adic spectrum of any Hooper pair is quasi-compact, then this implies that all these rational subsets are again quasi-compact because they can be written as the adic spectrum of another Hooper pair. And so this would imply that we have this basis for the topology there. Okay, so let me sketch the proof of the theorem. So we assume it's a rational subset, so let's choose Si and Ti such that this U is this rational subset given by these Ti's and Si's. And let's also choose A0 a ring of definition. And I a finitely generated ideal of definition. And let's consider any map from AA plus to BB plus such that on adic spectra it factors over U. And let's try to say as much as possible about EB plus. Then first of all, if you look at these SIs, then on this open subset they're required to be non-zero. And so, because this factors over U, it implies that the pullback of the S0s to B will be non-zero everywhere. And so by this lemma, this implies that the SIs are invertible. So we get a map A adjoin all the 1 over SIs to B. But then it makes sense to look at the elements Ti over Si. We can map them. But then this condition means that Ti over Si will have absolute value at most 1. And so this implies that Ti over Si, again by this lemma, will lie in B plus. Which is contained in B-circ, and I recall that the power-bounded elements could be written as a direct limit over all possible rings of definition of B0 of B. And so there are only finitely many such Ti's over Si's, so without loss of generality, all Ti over Si land in this ring of definition. And so we get a map A0 how do I want to do this? Well, yeah. Adjoin all the for Si, where I runs from 1 to n. Where this is to be understood as a subring of A. Invert all the SIs. So this maps to B0.
And A0 is chosen. A0 is chosen.
Sorry?
A0 is chosen depending on B0.
And A0 maps into B0. So because the image of A0 will still be bounded, you can arrange that the ring of definition also contains this bounded subset, this bounded subring.
These are issues to make that happen.
Yes. And so, what we might think is that this is actually pretty close to the universal example already. And so, so now we're trying to write down the universal example.
You haven't yet used the fact this openness condition on your deals, right?
I didn't yet,
Okay.
but I will explain in a second why I use it. So let's endow this ring there. With the I times this ring adic topology. Then we need to see that this is actually something reasonable. And we need to see that this actually defines a ring topology. So multiplication by any element is continuous. So let me just verify the crucial point where we need this openness condition. So I mean, in this ring, look nice. 1 over Si. So multiplication by 1 over Si should eventually be continuous, and so there should be some n such that 1 over Si times I to the n is contained in this ring.
Oh, you're not going to say define the ring topology on A?
Well, maybe I should say on A and
Yeah.
making this an open subring. Yeah, thank you. And to check this property, it's enough that I to the n is contained in ti times a0. Because if I multiply si by some element of ti, then they will lie in this ring. And that's very close to this openness condition we're imposing, that if you take our finite set ti times the ring, then it generates an open ideal, and so it would contain some such standard open ideal. Unfortunately, we only impose this for ti times a and not for ti times the ring of definition, so we need another small lemma, which says that if t in a is any subset such that t times a is open, and then t times a0 is also open.
Might not be easy. If T
well, I've written down a proof and it's not too long, so let's give it. So I can assume that my ideal of definition is contained in t times a, just because, I mean, some power of it will be in there, but I can simply replace my ideal of definition with the power of itself. And because I is finitely generated, this implies that there exists a finite set R such that I is contained in t times R, because any of the finite number of generators of I can be written this sounds really strange when I'm writing here. So I want this to be closed into something eventually. Such that, sorry. And so let's take some generators. F1 square of k. F1 square of k will be in there. So that's certainly okay. Also because I is topologically nilpotent, there exists some m such that, so this is a finite set, so any of those after multiplying by large props is ideal will be close to 0, so in particular in this ring of definition. And so then for all I points to k, fi times I to the m. So fi is contained in t times r, but r times I to the m is contained in t times I0. So this is contained in t times I0. And then we can sum this up over all I. And we get that I to the m plus 1 is contained in t times I0. And this looks like a proof. Okay.
Can you say again how you arrange A0 to map to B0 further back?
Well, the cheating way would be to simply intersect A0 with the preimage of B0, which would still be a ring of definition. I think I can also first choose A0 and then arrange B0 to be large enough, because the image of A0 will be a bounded subring of B, and there's a lemma that if you have a bounded subring and an open subring, then you can find a ring of definition which lies between the two. Okay. Okay. Back to this page. So this means that what we've done here is a reasonable thing, and so this means that is actually in this moment I'm considering non-complete rings. Is a non-complete Huber ring because it has this open subring, and because I was finitely generated, this is still a finitely generated ideal. And we still need this plus ring so that A 1 over Si plus the integral closure of the image of A plus to join all these Ti's over Si's. And then let be the completion of this Huber pair.
Equal closure in A1 over SI.
Sorry?
Equal closure in A1 over SI.
Yes.
So this might be really big, is that right? This plus thing?
This might get really much bigger, yeah. So it's a priori always hard to control this integral closure thing. So this is now a complete Huber pair, and it's not hard to check from the discussion that this has a desired universal property.
So the first term in that is, It's all confusing, because that guy is the completion of the guy without the t's in it.
Yes.
Yeah, but the topology is somehow highly dependent on the t's, and so yeah. So it's like in a tape ring, somewhere like if you have usual algebra of convergent functions on some disk or so, then you also a priori just have a polynomial ring, but then you specify the topology, and so. I think the topology, I think the notation is consistent. Maybe we'll see this later. And also, its spar maps isomorphically to U. For this, use that spar doesn't change under completion. And so you just have to check it for this more simple algebraically pair I wrote there. And so that the continuous variation factors over this ring, that just means that it's non-zero on the SIs. And then that's less or equal to 1 on this subring just means that it's less or equal to 1 on the TIs over SIs. Because if you have some element which is integral over something, it will still satisfy this less or equal to 1 condition. Okay, so then using this, we can now define the structure pre-sheaf. So well, I was already using this notation in the theorem, so it's the OX of U that was defined in the theorem. And in general, on a general W, it's just a compatible system of elements of on rational subsets. So you take all rational subsets contained in there. For X of U. And you can do the same for this plus guy.
So the theorem is that that's pre-sheaf on this basis of open sets really is a sheaf?
Unfortunately, not in general. So I'll say something about this in a second, but before that, let me just note the following proposition that for all open subsets, one can recover this OX plus of U from the OX of U as being those functions that such that for all x and u, the absolute value of f at x is at most 1. Which is really just this property reduces to this, formally to this property for u being the whole thing itself, where it's set at a plus, this kind of thing. But this says in particular that OX plus is a sheaf if OX is.
So in this definition, you haven't really defined OX plus yet. So is it sheaf? So
well, I mean, just put a plus everywhere in this definition.
Okay.
And so what Huber proves is that in essentially all situations one usually cares about it's a sheaf. The first is kind of stupid. It's okay if A is discrete. So if A is discrete, also all the OX of U's for all open subsets U will be discrete. So there will be no topology on the rings anywhere. Which is a bit different from what you sometimes see for Berkovich spaces, where even if you start over a discretely valued field, the structure sheaf on this Berkovich space might introduce some topological rings. This doesn't happen for adic spaces. So this is some of this, more or less a scheme setup. It's also true if A is finitely generated as an algebra. Over an Assyrian ring of definition. That includes in particular the case of formal schemes. I mean Assyrian formal schemes, I should say. But then there's a third class when A is Tate, so we are more or less in the rigid setup. And then again you want some Assyrian hypotheses, but you need something that's slightly stronger than being Assyrian. What's called strong in Assyrian. So, what does strong in Assyrian mean? It means that any Tate algebra on any number of variables, which is a set of sums AI times t to the I, where the AI are elements of A which go to 0, meaning that for any epsilon there are only finitely many, I mean for any open neighborhood of 0 there are only finitely many which do not lie in this open neighborhood of 0. So that this algebra is an Assyrian for all. Why is it worthwhile to have, or what are cases covered by 3 that are not covered by 2? So the prototypical example would be where A is something like CP. So this does not have an Assyrian ring of definition because the ring of definition would be like its ring of integral elements, but that's not an Assyrian. So it's a valuation ring which is not discretely valued, and those are never Assyrian. So for example, you have this increasing sequence of ideals given by fractional pairs of P. But any Tate algebra over a CP is Assyrian. So if you want to do rigid geometry over non-discretely valued fields, you're really in this case 3.
So do you want n greater equal to 1?
Well, I want A itself to be Assyrian as well.
Oh, okay.
But probably follow, I mean, I guess the condition for some n follows from the condition for any bigger n because you can just kill all the extra variables.
Did you ever have A Noetherian but not to this Tate algebra? Did you ever have A Noetherian but not to this Tate algebra?
Sorry?
Adding this Tate algebra, could it ever kill a Noetherian property which was there in A?
Yeah, it's not so clear. So it's, I mean,
Yeah.
I think it's an open problem to find an Assyrian ring which is not strongly Assyrian. But it's also not so clear how to prove it because. Yeah. So if you have an Assyrian ring of definition, it's okay, but in general, it's not so clear. I mean, there are even examples where this would be interesting to know. So, in the context of the Falk-Fontaine curve, for example, one has examples of such rings A which are Tate and which are also known to be Assyrian, but which are not known to be strongly Assyrian.
So is the theory unworkable if OX is only a pre-sheaf and not a sheaf, or does it try to work it anyway?
Well, I will explain one kind of definition one can still make of spaces when the pre-sheaf is not a sheaf. One has to be a bit careful.
Are you thinking of this as a sheaf of topological rings, or just as a sheaf of bare rings? And are you asking for
Sheaf of topological rings, yes.
So in this case, you have some kind of compatibility that if you have an open cover and a sequence of elements can satisfy the compatibilities converging on
Well, essentially just means that if you have a covering of U, and so it just maps the product CUIs, then this map here is true.
And this is true in all these cases.
This is true in all these cases, yes. In all these cases, even much more is true. So you can even define coherent sheaves, and they will have vanishing higher cohomology groups on affinoids, in such an affinoid space, and so on and so forth. So I think for the rest of my lecture, I want to explain an example. So the p-adic spectrum of this kind of thing.
Well, defined a category yet?
We have not defined a category yet of p-adic spaces. I thought I would first explain the example and then do the definition of p-adic spaces next time, but I think everything I need for the example is pretty much in place already. So I can define an isotopological space, I can say what the structure, sheaf is, etc. So
You won't be able to explain why the generic fiber is
well, I can.
fiber product in the category.
I think I have enough available to say what I want to say. So here I consider ZPT with a p-adic topology. And so this clearly falls under 2. So let me first try to describe the topological space. So there is a unique point, which is somewhat the point you. So if you regard this as a formal scheme, it's just a point, and so this point still survives to the p-adic space. Let's call this. Let's call it my example X, and so there's a unique special point S and X. It's a unique point which property? The property is that the kernel of S is open. The kernel of the valuation at S is open. And explicitly, what is it? So we have the value at S. So because it's supposed to have open kernel, some power of P and Q will be in there, but then because the valuation, this whole ideal will be killed. And so it will necessarily project onto FP. And on FP there is just this one variation, which is 0 and 0 and everywhere else it's 1. And so the interesting part, let's call this maybe y, is x minus a special point. And so in there, all points have non-open kernel. That means they're what's called analytic. And let me in fact make a short digression on this notion of analytic points. So a point is non-analytic, and it's the kernel of X. The associated valuation, not sure what's the best notation, is open. And so this means that it comes from some quotient ring A mod I, which is discrete. So it comes from the usual scheme setup. And so otherwise we call it analytic.
So does this mean it's in the image of spec A?
It's no.
No?
So I gave you the example of SPA-Z Z last time. And SPA-Z Z had all these points corresponding to the points of the spectrum, but then it has these other p-adic variations, which don't really come from the spectrum.
And they're also non-analytic.
They're also non-analytic, yes. Because, so whenever you have a point on the adic spectrum of a discrete ring, its kernel will always be open because everything is open, and so they're all non-analytic. So let me describe those analytic points a bit. So if you have an analytic point and I in A0, some as usual, ring of definition and finally generated ideal of definition, then there exists some, then because X doesn't vanish identically on I, otherwise the kernel would be open, so there exists some function in I which is non-zero. Let me call gamma its absolute value. It's some element of this value group of gamma. So it's the value group at X. And then this gamma actually has an interesting property, namely, whenever I have another element gamma prime in gamma, then there will exist some sufficiently large n such that gamma to the n is smaller than gamma prime. So in some sense the powers of n are co-final in all elements. So why is this?
So when you write gamma x, you now always mean the image of the value.
It doesn't actually matter for my discussion, but yeah, a good idea in general. So why do we have this inequality? So indeed, we ask that our variations are continuous, so the set of all G and A such that the absolute value of G at X is less than gamma prime. This is supposed to be open. So contains f to the n, as f is topologically nilpotent for n big enough. But then gamma to the n, which is the absolute value of f to the n at X, is less than gamma prime. And then there is something you can say about totally ordered being groups which admit such an element gamma. So namely, what you can essentially do is compare gamma prime against all rational powers of gamma. Well, the rational powers don't exist, but you can compare two integral powers of gamma against integral powers of gamma prime. And what you get this way is that there exists a unique order preserving map gamma to the positive reals such that gamma is sent to any pre-chosen element, say a half. And so the kernel of this map would be elements which are in some sense infinitesimally close to 1. Also,
I can't read the first in the parenthesis. What's the first word?
kernel.
Kernel. Okay.
The kernel is this map of being groups. Also, this map to the positive reals is essentially independent of the choice of gamma and the choice of a half up to rescaling the positive reals. So let me leave this as an exercise. So, in particular, any analytic point x gives rise to an x tilde which takes A to the non-negative reals by just composing with this map to the reals, and this is so the equivalence class of x tilde is well defined. And then this x tilde will in fact be the maximal generalization of x. So what happened is that for a general point we allow a higher rank valuation group. And so what happens here is that in general we can forget some, in general this higher rank value group may contain some infinitesimal extra information which we're just forgetting under this projection here. So, example of x as value group positive reals times some gamma to the z, where, well, this is not this gamma there. R is less than gamma less than 1 for all reals which are less than 1. And x tilde is just the thing where you project the first factor. So why is this a generalization? So if U, some open subset of the form, it contains X, then these conditions here, they will still be true after I projected this positive reals factor. So. And so this means that x tilde is a generalization of x. And after that, there's nothing more you can do somehow. So. Okay. This is an exercise. So in particular, this means that if x is an analytic point, and I denote by k of x the completion of A modulo the kernel, this valuation at x. With respect to this valuation, which vectors of it, then this gadget here will be a complete non-Archimedean field. Or let's just call it non-Archimedean fields. Where what I mean by non-Archimedean field is the following. This is a complete topological field K. Whose topology is induced by a non-Archimedean norm.
Stupid question, how do you not get an order in the field? How do you know you get the field itself?
Do you
You
need
give a parameter maximally.
Sorry, I want to take special here, sorry. Yes.
And
So if you take x tilde, is it a field already?
I think this should be a field, yes.
If you take x tilde instead of x.
Take x tilde instead of x. No, I mean k of x will be the same as k of x tilde. Because the topology induced by this valuation, it will not depend on this infinitesimal condition.
Yeah, but if you take x tilde instead, is it already a field? Without taking fraction?
No, I mean if A was, for example, ZP power series T guy there, then or if A is ZP and X is the usual p-adic valuation, then you don't mod out by anything. So this is just ZP still, and if you complete with respect to the p-adic valuation, still have ZP. So.
Is a discrete K allowed in this definition? Is a discrete K a topological non-Archimedean field?
No, I don't want my guys to be discrete. So if it was a non-analytic point, then doing the same definition, I would then end up with a discrete field. And so, but I think I want to reserve my terminology for non-Archimedean fields to be non-discrete. And so.
One question, in your exercise, this projection sends gamma to 1/2,
Yeah.
but this projection kills gamma. Or is this
No,
gamma?
this gamma is not this gamma.
That's
Sorry.
not that gamma.
I don't know, maybe delta or something. I don't know.
But then what role is gamma playing in this group?
1/2, 0.
Well, so I should take 1/2, 0 if I want such an element there.
But then delta powers of delta don't get smaller than 1/2.
Yes, so they are killed. Yeah. So I compare all integral powers of delta against all integral powers of gamma, and I will see that somehow this will always look very close to the 0th power of gamma. So it will be sent to 1 in this.
What powers of delta? Gamma's playing a role of 1/2.
Yes. It's 1/2, 0, 1.
Oh, sorry, gamma taken.
Yeah. Oh, okay. Got it. Great. So back to the example.
So you say that x and x can define the same topology on it?
Yeah. Just because they somehow only kill infinitesimal information.
Uh-huh. And in what way does that make them equivalent or not equivalent?
Well, I mean, equivalent means that the order relations they define is the same, but I mean, this defines a stricter order relation because there are some elements whose variations may be delta, and another element whose variation is 1, and so they are different here, but they will be equal here. So back to what I just called y, which was this x, which I recall was the adic spectrum of z p per series t. Remove the closed point. And so all points here are analytic. And so using this one can actually define the funny map on this y. So there is a unique and continuous map. I have no idea what to name it, so let's name it, or maybe not F, kappa. From y to 0 infinity, including 0 and infinity. Characterized by the following property. Kappa of some point x will be r, if and only if for all rational numbers greater than r, and I hope I checked all my normalizations correct. I mean, you can compare integer powers of these natural parameters p and t on the space, and so this is what is supposed to give you this map. And so if m over n is less than r, the reverse inequality is supposed to be true.
Yeah, m on the right.
Thank you. Yeah.
The map is surjective.
The map is also surjective, yeah. Let me sketch why this is true. So let's first of all check that what we're asking for is well defined and also unique. So what happens is that any x and y is analytic, as I said, and so it defines a map x tilde, or absolute value at some x tilde, from ZP power series T to the non-negative reals. And this will always have the property that either the absolute value of P at there is non-zero, or the absolute value of T is non-zero. And so, I hope I did my algebra correctly, but I think if the absolute value of P is non-zero, then the formula is that kappa of x will be the logarithm to the base absolute value of P at x tilde of the absolute value of T of x tilde inverse, which should give you an element which might be 0 but is not infinity. And here, so the contrary is supposed to happen.
What's the exponent? T to the x tilde and then the exponent?
That's just an inverse to the minus 1.
So how do we get infinity? How do we actually get infinity with this reevaluation? Only here.
Well, if T is the absolute value of T at x is 0, then you have the logarithm of 0. I suppose it's minus infinity or whatever. And so its inverse should be 0. Well, I guess because we are taking the logarithm with respect to a base which is less than 1, it's actually plus infinity. So if you take the inverse, it's 0. And so, yeah. So kappa of x in particular is 0, if and only if it's 0, if and only if we are in the first case, where then the absolute value of T at x tilde is not 0, which is equivalent to the absolute value of T at x already being 0. Which means that x vectors through the map from ZP power series T to ZP. But then we assumed it's not the closed point, so it's necessarily the p-adic absolute value, which goes to the non-negative reals. So there's just one point which is sent to 0. And similarly for the other end.
And I suppose it cannot happen that both are non-zero, right? Because it's analytic, right?
It can't happen. Of course, it can happen that both are non-zero.
Okay.
That's, I mean, except when kappa is 0 or infinity, both of them will be non-zero. I mean, so the picture is that. So what's this adic spectrum? So it has this closed point, and then it has a locus where p is 0, and that's this special point, and then one generic point, which is the one I've just written down. Then similarly, there's a locus where t is 0, which again has a special point, and then we'll have one generic point. And then there is a whole something big in between. So you should consider this whole thing as somehow being like the spectrum of a complete two-dimensional local ring. After all, ZP power series T is a complete two-dimensional local ring. You have this coordinate axis inside, but then there is all this generic part. And so this is somehow sent to when T is 0, I'm getting 0, I think. I mean, sent to this line from, you have infinity here, you have 0 here. Okay, I want to say one word that it's continuous. And so say if you look at the pre-image of an open subset of the form m over n infinity, then this is given by, well, we can look at this. So m over n is less than r, then we are supposed to, it's a set of all x such that, well, let's reverse two terms. I can pull the m inside. And then actually, the set of all such x in y is also the set of all x and y, where I also require that this is non-zero, the second term, because if it was 0, then also the other term would have to be 0, but there are no points where both are 0. And so this is. And then similarly, you can do it for intervals which start from 0 and go to some rational point, and then everything else can be similar, gotten from those.
Is it obvious that those two formulas define the same number when p and t are both non-zero?
Yes? I mean, the log A with respect to the base B and B are non-zero is the same as the inverse. I mean,
It's log A divided by log B if you choose it.
yeah, okay, yeah. Maybe I should write log A divided by log B. Okay, so what did I want to do with all this? So in particular, so let me introduce the notation. So for I contained in 0 infinity, that yi is this image of I. And so thus y0 leave out infinity is the locus where p is non-zero. As you can also check from this picture, so there's only one point where p is equal to 0, and that's the point which is sent to infinity here. And so that's the generic fiber. So, and so note in particular that this generic fiber cannot be affinoid. It's not even quasi-compact. Because any quasi-compact open subset would have to be in the pre-image of some closed interval. In fact, let me expand on this comment. So, in fact, one might think that this generic fiber should be the adic spectrum of this ring you get by taking ZP power series T and inverting P. However, this is not a Huber ring. So first of all, I have to say what it should be as a topological ring. And so the only thing it could be is a direct limit topology. Of all the p to the minus n times CP power series T, while endow these with a p-adic topology. It's not a Huber ring. Why not? So one reason is that if he takes this topology, then ZP power series T as a subring, which you would probably like to be a ring of definition, it's not open. Why not? So one way to see this is that if you take P inverse times T to the n, then this goes to 0 as n goes to infinity, because it goes to 0 in this open, well, in this here, and it's a direct limit topology, so it converges to 0 in here, then it converges to 0 in the image. And so some element of this would have to lie in the subring, but it doesn't.
So is this generic fiber really the fiber product in the category?
It is a fiber product in the category of adic spaces. So I guess I have to stop in a second, but let me just make a few more comments. So another way to see that this can work is that CP power series T invert P. It would have to be a Tate ring. As P is supposed to be topologically nilpotent at a unit. But we've seen that for Tate rings, any ring of definition will have ideal of definition given by one element. So thus, any ring of definition as ideal of definition. P, or maybe P to the n, if P is not in the ring. But we were trying to get some situation where this was p-adic for two different elements of T. And so this means that to get a finite subset of this generic fiber, we need to impose some condition which somehow means that some power of T will again be smaller than P. And that's equivalent actually to exhausting by all the y0. And I think I have to take the interior here to be completely honest. Which actually are then the adic spectra of, well, the ring you will get is QP adjoin T and T to the n over P. And then the correct ring of integral elements, which I guess is really what you think it is. And so imposing such an extra condition is precisely this kind of thing we wanted when we defined rational subsets. So maybe we can also, of course, trivially impose the condition the absolute value of p is less than or equal to p. And then p and t to the n generate an open ideal. And so that's why we made this requirement when defining rational subsets. Okay.